Perfect. Welcome. This is the third take I'm making, um, as I'm having some issues with the with Zoom, but let's see. So this should be the right take, hopefully. Okay, everything's working. Perfect. So this is the third video where we're going to be covering the Dankrad blog post on KZG polynomial commitments. So the idea is to go over the theory again for all of these videos. I'm making the idea is to explain how EigenDA works, what's the theory behind this at the mathematical crypto level. Um, so we already covered in the two previous videos the how like elliptic curves and then the pairings. So for this one, we'll assume that you've watched those videos and we'll treat kind of the pairing as an assumed concept, which we'll be able to use as a black box. So if you haven't watched them, please go and watch the other ones. Um, so this is kind of the central piece of EigenDA, the KZG polynomial commitments is very, very important. A lot of, most of our properties kind of rest on this construction. Um, and and so today we're looking at the theory for how this works. So it's purely mathematical. And in the next video, I plan to actually look at, the implementation for how do we make these things actually fast. So okay, let's jump into it. Um, First, so if we look at an intro, so what he's saying is that right, so he's not trying to be kind of mathematically rigorous, which is kind of funny because like I'm sure for a lot of people he's already too mathematically rigorous, but basically there's no proofs in here. It's just giving the intuition. Um, so what is KZG polynomial commitment? Basically, we want to compute a commitment to a polynomial. Right? And what does this do? Is just you have a polynomial, you commit it into this commitment, and using this, you can later reveal um, openings. So we call them open at any position. So if you have a polynomial that we can say, you have a polynomial p of x equal to some I equals 0 to n of pi x to the I, you can reveal, you can prove that pz equals to y or whatever. Um, so that's the gist of it. So it's called a commitment um, because having sent the commitment value and elliptic curve point to someone, the verifier, the prover cannot change the polynomial they are working with, right? So for those of you that know this kind of, this commitment, this is the binding property. So a commitment mathematically or cryptographically speaking has two properties. So the first one is the binding property, which just says if I send you a commitment, it's binding to the actual item that is committing to that. So there's no way to, to reveal something else. So that it's the only thing that can bind to this. Um, and two is typically there's also a hiding property, which means that basically by sending you this commitment, I am and even going through a reveal process, I am not revealing any information as to what the actual, secret or polynomial in this case that I'm holding. I'm not revealing information about that polynomial. So the hiding property for us is not important. Actually, what we care about is just like in ZK proofs is more like the succinctness. We care about the succinctness, which we can see, I guess, as a third property of this, meaning that the commitment is very small. I can and you can also a verifier receiving the small commitment can in a very fast amount of time succinctly verify the proof and convince itself that indeed the data received belongs to the polynomial. Okay, so it's kind of still very abstract. So he goes on and compares a KZG commitment to Merkle trees, which I will assume everyone working in crypto knows about. So, but very quick, a Merkle tree, what cryptographers call this one is a vector commitment as opposed to polynomial commitment, which means it commits to, a vector. So you just, where if you have a Merkle tree is just this like this, right? So you have H1, H2, hash 3, hash 4, which are the hashes of these. So if you have element 1, you hash it, element 2, you hash it like this. and then you just recursively hash kind of the hashes like this until you get the root to the root hash. Um, and then the root hash is your commitment to this entire vector of elements E1 to E4. And you can always reveal kind of a single item, let's say E1, by giving sending as proof the H2 and the H3. And then with this, and this, you can prove that the E1 does indeed belong to this commitment tree. That's the idea for the Merkle trees. So we'll see how a polynomial commitment generalizes this. So he says that actually, okay, what he says is interesting. We can actually make a polynomial commitment out of Merkle trees. Um, and the way you do that is just by taking the polynomial, you take its coefficients and you will encode them, here at the leaves of the Merkle tree. So that's what he's saying here. And then if you want to reveal the polynomial, so you want to prove that, let's say, pz equals y for some z, the prover can do so by sending the verifier all the pi's and the verifier computing that the pz is indeed y. So actually, in this case, you don't even need a Merkle tree since you're giving all of the leaves. You could have just committed directly, like the hash is equal to the hash of the concatenation of all those elements because anyways, you're revealing all of them. Of course, he goes on to say that this is kind of extremely stupid polynomial commitment because the commitment size, okay, the commitment size is still a single hash, so that's good. But then to prove an evaluation, the prover needs to send all of the pi. So the proof is already linear in the degree of the polynomial. Um, and then the verifier also needs to do linear work, which is the bad part. Of course, it's also not hiding. It's not hiding because I have to reveal the entire polynomial. I can't just reveal a single point of that polynomial. Not that it matters, but I mean, not that it matters for us. Okay, so if we compare this and we look at the other Kt scheme, again, the commitment size is one group element. Um, so in the case of this is the BLS 1231 is the curve used by Ethereum for 4844. It's 48 bytes. In the case of EigenDA, we're on the curve BN254. So our commitment is actually a G1 point, which is 32 bytes as a smaller curve. And then the proof size here is actually independent of the size of the polynomial, as it's a single group element, right? So this is the interesting part. Not only when I commit, it's small, but when I send you a proof to reveal, it's also very small. So that's kind of one of the most important properties. This is actually the succinctness property that I was mentioning earlier. And also he mentions that verification is also independent of the size of the polynomial. So not only I'm only sending you a single group element, but also the amount of work that you need to do to convince yourself that the py equal to z is also very small, actually constant. And then this scheme mostly hides the polynomial. Yeah, so it mostly hides. There are ways that, again, this is not super important, so we can go over this. Okay, so this is kind of the setting. Now, how do we actually construct this? We use pairings. So here he refers to Vitalik's blog post on the curve pairings. So that's the other article that I covered in the previous video. So if you haven't watched it, I recommend that you do. So it's all the typical notation here, where he uses this. So x1 and x2, I believe I went over this notation, but right. So this kind of, you can see it, embedding x. So x is a scalar field. You send it to you kind of embed it in the group just by multiplying g, or by adding g to itself x number of times. Because xg is equal to g plus g x amount of x number of times. Okay. So this is that. You might have, oh yeah, so there's a bit of a weird thing here. He says let P be the order of G1 and for any X in the field FP. Typically FP is actually the ambient field size. Um, so typically this would be FR. Typically R is the order of the group, which is actually smaller than the order of the embedding, because G1 basically is kind of embedded inside the FP cross FP. But the order of the curve, meaning the amount of points in that 2D space, is actually R. So, but anyways, I mean, it doesn't really matter, but I was just surprised to see the P here used. Um, Oh, as I'm looking at my notes, I do see just here that I forgot to say that. So apart from the properties that we saw above, it is actually possible to combine proof for any number evaluation into a single group element. So this is actually another. It's like even more succinct proofs. So this is similar to BLS signatures, which you might know of. And of course, both rely on the pairing. So yeah, it's more the structure of the pairing that allows you to do these kind of things. So you can add the group element inside the group, and then you can with a single pairing or multiple pairings, but you can prove all of them. But the proof still is a single element. So we'll make use of this, and we'll see at the end of this article. This is also very important. Okay, so getting back to this, this is also kind of as I've noticed, but not that important. Um, okay, so here's another assumption. So we mentioned, okay, so in the previous video, we talked, okay, you start with an elliptic curve, all that it is kind of a group with an operation. In order to get some other properties, you use a pairing. So you add to that kind of, instead of having a single group, now what you have is, well, you have kind of a set of these three groups which are related by, the field extensions, whatever. You have G1, G2, and GT, and you have a pairing structure between them. So that gives you kind of the ability to do some kind of multiplication, quote unquote. And so that is enough to do a lot of interesting things, but it's not enough to do what we want, which is to commit to a polynomial. So for that, we're going to need this extra kind of set, which is called, it comes from the trusted setup. This is the last kind of, algebraic structure thing that we're going to need to add. So we're going to have these three groups, the pairing relating them, and then we're going to have the trusted setup, which are these SRS points. And using all of this, we're going to be able to derive everything that we need. Okay, so what is a trusted setup? I'm also going to assume that most of you are familiar. I'm not the best person to explain how the MPC stuff works for it, but effectively what it really is just there's a secret S, which is a field element. There's a secret S. And so you take this S and then you raise it to all powers up to some, 2 to the some high power. So we kind of create this. And then, we basically destroy the S and nobody knows about the S. So we're left with all of these elements inside of our group, namely, that's this extra structure that I was saying. So we have S, um, S1, S squared, S cubed, all of this until let's say S to the 2 to the N, so for some high N. We have all this and then we destroy S. We forget how it happened, and people do this via, secure multi-party computation. So if you trust that at least one person of the group was not colluding with everyone, there's no way to kind of reconstruct the secret. But he explains here you could do it with some, simpler, kind of more stupid ways, at least conceptually. But the important part is that once we have all of these elements, these SRS groups, these SRS points in the group, I give you all of this, and still, because you're not able to, because the log problem is hard in an elliptic curve, you're not able to, even though I give you this, you're not able to get back S. And then there's kind of a stronger Diffie-Hellman property, which is even though I give you all of these powers of S, it's still kind of not enough information for you to be able to reconstruct S. So S has to remain secret at all times. That's kind of the most important thing. Um, Okay, so what else does he say here? He says, you can't do this just by selecting. Right, okay, so yeah, so I mean, right. Um, it's impossible to compute S squared without knowing S, right? So again, he's just saying, basically the only way to do this is really to have this S, which unfortunately you need to have. you need to start with, you embed, and then you kind of embed all of its powers, and then you have to, and you forget about S. There's no other way without creating this S that exists. So that's why the S is also sometimes called, I forget what it's called, like a toxic residue or something. And it's the thing that you hope that was actually destroyed, nobody can recreate. Now, once you have this, okay, and again, what I was saying, so elliptic curve cryptography basically tells us it's impossible to find out what S is without from the trusted setup group elements. Okay, and then elements they are given. So, okay, there we go. Okay, so let me take a awkward sip here. Okay, so a little reminder of what we saw in the previous video, but you can think of the the field is here, right? Kind of just a field with the plus operation. It's modulo, like a clock arithmetic, just around going around the clock. The G1 we also picture like this, although it's an elliptic curve, so whatever, you can picture it like this, but it's whatever. And so G1 is your elliptic curve with the point at infinity with the plus operation in the field. Of course, you can do both plus and multiplying. Um, and then we have these commutative diagram, meaning that you can using this embedding of the field element into G1. Um, this embedding is actually commutative with the addition. So whether you do your addition in FP or in G1, you can go this way or you can go this way, and you'll always end up at the same result, which is really nice, right? It means homomorphic, meaning it keeps the structure of the addition, this embedding into G1. Um, this is very useful, but what it doesn't do is that it doesn't keep it doesn't keep the second operation of the field, the multiplication. Because if you multiply here a times b, and then you embed this into G1, there's no way to embed a and b and then do some kind of operation to get back at a times b. Because there is no multiplication in like there is just no multiplication on the group. Um, so if there was some other structure, blah, blah, that's when we talk about fully homomorphic. He also mentions this somewhere in the blog post. Okay, so now that we have this, I want to extend this basically to, okay, so what is the trusted setup? Really quickly, I guess visually, you have your field, and then, this is the field FP. And then we take, I don't know, let's say we start with S. This is our first S that we chose. And then you just kind of raise it to power. So you get S squared, S cubed, S4, S5 like this. And you take all of those powers just by going around the clock. And then we embed all of them into the group. So with these guys, we'll also arrive somewhere, in some random places like this. Like this. And then you get all of those powers. And then these guys are kind of all destroyed. We forget about them. And so we're only left with this set of points. Okay, so what does this allow us to do, which is the very important thing that we needed from the start. So with this extra structure, we can now, I will say, we can now extend our commitment to polynomials. Um, okay, so I guess what I was calling commitment here is this function, this embedding function that is the function from the fields to the group to G1. So this right now we already have this commitment, right? So I give you an element of the field, and it gives back an element of G1, which has the binding property. Also, because of the log, I can't come back, but I can reveal it just by giving you the element. So we have this, but okay, so if we do this, so let's say FP, so we'll draw again a commutative diagram. or I guess no, sorry, in this case it's not commutative. So okay, we have G1, we add the SRS point, so we add this extra structure, and then this will allow us to lift basically this embedding, which means just define it on the polynomials. So this is the notation that we use for the polynomials defined over FP. So basically polynomial where the coefficients, uh, the coefficients and the values are defined on top of this field. So we have this, and then, okay, so what we want is we want to define, how do we define this? Basically, we want to be able to, I give you a polynomial and you can also embed it into G1. So how do we do this? Again, we need to kind of use this guy and we need to do something here. So how do we do that? Well, we have our SRS points, right? So this one we will call embedding using the SRS. And so here we will define this to be sum of PI SI. This is how we define. Um, so I guess how could I say this? I could say, let me redo this by saying that we define. So if I have a polynomial P of X, which is equal to sum PI XI, I will define the embedding PX SRS. I'll define this to be um, um, the embedding of, oh, right. Okay, so this is how you define. So you define P of X, its commitment is defined as the commitment of P evaluated at S. So the value of the value the polynomial takes at S, you take that value, boom, you send it to G1, and that is your commitment. And why can we compute this? Because this is just equal to some PI SI, and by the property is just some PI of SI, right? And these are all of our SRS points that we have. So because we have all of them, now all we're doing is this is a scalar multiplication, and then we have an addition of items of group elements. So this is also what we call an MSM for multiscalar multiplication. So by doing this, basically, I get I can now commit to polynomials. Okay, this is how this is kind of the definition for how it works. And if I go back a little bit, this is also what he's talking about here at the top, at the bottom, sorry, they can only do certain computation, blah, blah. Um, So here, he just has the exact same, this part at the bottom. So this thing right here at the bottom is exactly what I just explained. Okay, nice. So now we have our definition for a commitment, for the commitment of the polynomials. So let's see what we do with this. I see. Okay, so I forgot about this. So this part, I said there was no theory. I guess there's a little bit of theory, but the Catholic commitment. So he just now, so we've defined it. Now we need to prove that it's a commitment. What does this mean? We need to prove that it has the binding property. We also need to prove that it has the hiding property. We don't care about the hiding property, so let's just quickly see why it has the binding property. Right, so this is the definition we had said earlier, just above. And okay, so what he mentions here is that okay, you may ask the question, could the prover without knowing S find another polynomial? Right, so to prove that you have the binding, you basically have to say that there's no pre-image attack. I can't create two polynomials. If I have a commitment, uh, if I have this commitment to P, I must not be able to find another Q of X that would commit to the same place. So how would this be? Basically, I need to find another polynomial Q that would evaluate, right? So we said the commitment is what? It's just the evaluation, the embedding of the evaluation of P at S or Q at S. Of course, if we knew S, we could just like, I would know P of S, and then I can just construct any other polynomial, Q of X, that passes through that S. That would be super easy. But as we said, S is a secret that nobody knows, so I can't do that. So the best that I can do is to construct any other polynomial that would basically agree with P at as many points as I can. Um, but because of, polynomials are kind of rigid objects, the best that I can do is for a polynomial P of degree, let's say degree D, I can make Q and P match it at most D points. And then, so what does this mean? It means that there's like, this famous, what all that he's explaining here is basically the Schwarz. How do we write this? Schwarz-Zippel, Schwarz-Zippel lemma, which basically says that um, kind of that, the probability of having two polynomials agree on the, on a point, if I'm sampling this as this the the space kind of the field is large is basically zero. I'm botching this, but effectively you can see that he argues here with like more kind of a clever wording that so our set of SRS has 2 to the 28 points. This is the number of of SRS points that we have. This is also the one that we have for EigenDA. Some SRS sets are much smaller, but we have the largest actually set in existence for the curve BN254. But the actual space of FR is it lives there's 2 to the 256 possible points. Um, so that means even if I create a Q of X that agrees with P of X at 2 to the 28 points, which I'm able to do, because I don't know the S and it's kind of randomly sampled, the chance that it lands in this set 228 is infinitesimal. It is basically this. Um, so in all likelihood, I will not be able to create another polynomial. So that's why we have the binding property. That's what this is saying. Um, okay, so moving on. Um, okay, so now we get to the interesting part. So now we have our commitment. We've proven that it's binding. Now we need to open it. Um, so by opening it, it means, it's the verification part. So I will send you something that will convince you that um, he doesn't mention it anywhere, but I will convince you that, f of z is equal to y somewhere. Um, okay, so that's what he's saying here. We're still missing the ability to open this commitment. Of course, without actually sending the whole polynomial over to the verifier, right? So we're trying to do better, as we said, than the Merkle tree commitment approach. Um, compute. Okay, so here he's saying we can also do some arithmetic. So on the polynomials, um, right? Okay, so okay, as I said, so if we go back to this definition here, right? So what this commitment on the field has is it respects it's commutative with addition that I said here. So we have this commutative diagram. Um, we don't have this. We don't have uh, commutativity with multiplication, of course, because pairing the group doesn't have a multiplication. But we have this pairing structure, which gives us some properties that are like multiplying, which are enough just for doing verification. So now what we're gonna see is that we can extend this commitment definition to the space of the polynomials. And again, this will again respect the commutative diagram for addition, and the pairing will also be able to give us the same kind of multiplication of polynomial ability, which is what he's saying here. So now he's saying he just introduces this new notation um, here, um, which is that. Um, So when we can do that, we can use some color ones. Ah, right, I see. Okay, so here he's actually just talking about the lower level, kind of the same pairing that we saw in the previous article with Vitalik, that you can have this notion of multiplying. So the pairing, so what he defines here is that if you, so you have A1 living in G1, you have B2 living in G2. Um, and by the pairing property, because it's a bilinear operation, it kind of amounts to this. I actually like to write this as AB e to GH, and to keep the same additive structure also on the third group GT, but it doesn't really matter. Um, and so here it's a definition. So he defines basically taking this is the identity element, or I mean, not the identity element, but the generator, we'll say, of this third group GT. And this, if you raise it to the power of AB, now the notation he used for this is just ABT, right? So we're used to this notation like A1, meaning you embed uh, A into the first group, and we're used to the same for group T. Now he's saying, oh, now we can also do this AT. Let me explain why this is interesting and why it's also kind of a little bit surprising. So we have the commutative diagram for the plus. What we're looking for is a similar kind of idea, but um, for multiplication. So if we start again with a similar diagram, let's say we start with FP, and we have let's say A and B here, right? And we know that we can kind of push those into their groups. So let's go to the G1, G2. And here we have A1 and let's say B2. So we can do this. Um, we also have this other group, which is GT, the third group kind of relating the pairing. And how is it related? It's related by this equation that we just saw at the top. It's related by here. Um, so what this kind of says is basically this. So you have A, B, T. So this is, if I take A and B, I multiply them together, I get A times B here, and then I can just push it via this other embedding here, that we've defined as, just this is defined as being E of GH. So you take the generator of G1. Actually, I also like to call them G1 and G2. You take the generator of G1, generator of G2, you take their pairing, it gives you an element inside GT, and that becomes your kind of the generator that you use for the group GT. And then you can take that and raise it to the power of A times B. And this, doing it this way, will commute with going the other direction. It will commute with this, like kind of, taking the pairing here. Um, So this is one, two, this is T. And yeah, these guys kind of come together, right? Um, so yeah, that's kind of the crazy thing. So this is defined as this, but the fact that this is actually equal, so you have commutativity of E to of A1, E2. This is kind of the very interesting part of why we use these pairings. So it gives us a commutative diagram. It's just that we can't stay inside the same group. We got to go to this other group GT, but we get multiplication, which means we'll be able to verify some properties of the polynomial. So I guess another diagram that we could use for this is if you're used to something like, the elliptic curve FP. Um, you can draw the elliptic curve G1. Not that it really helps, but sometimes another picture, right? So you can embed, you have A, B, and then you can multiply them like this, A, B. And then this one you can just push here. And the result of this is the same as instead, embedding A here, embedding B here, and then taking the pairing to go like together. I don't know how to draw this, but like combining these. to go like this. Um, okay. Okay, perfect. Um, so now I've kind of explained why we say that the pairing gives you multiplication abilities in some sense. Actually, what it's going to give us is the ability to verify a multiplication in the field, and that's going to give us kind of these proofs. Okay, so this is the meat of the argument. So now let's say we want to prove that PZ equal to Y. So we're trying to reveal one data item of the polynomial, namely Y. Um, then we use the polynomial Px minus Y. This polynomial is clearly zero at Z. So we can use the knowledge about the linear factors, and then and then we divide Qx. You divide this by x minus z, um, which is equivalent to saying this. And then the proof for this fact will be it will be the commitment of QS, right? So the proof pi is Q uh, is the embedding of the evaluation of Q at point S. So let me unwind all of this. Um, so okay, what's first? Let's just like expand on this in case it wasn't clear. So you have here we have, let's say, a point Z, and P, let's say, is equal to Y at Z. So let's say, we got some kind of polynomial like this. Let's say this is our polynomial P of X. Now we compute P of X minus Y, which gives us this other curve which goes through zero, right? So this is P of X minus Y. And because this polynomial is equal to zero at Z, we know that we can rewrite it as this factored form. So this Px minus Y is this polynomial. You can just factor out x minus z, um, because x minus z is just a linear polynomial going through zero at the point z. Um, so so then you get this other. So this q of x is just a degree d minus one polynomial because we factored out um, the x minus z kind of linear term. So that's all that it is, right? It's just kind of q of x has the information that p evaluates to y at z in this kind of a form. Um, okay, so hmm, I'm trying to see how I can make this easier. So I think okay. So let's see what he does here. Kate proves evaluation PC is defined as this. Okay, so this is our okay. So let's see what he does exactly, and then let's have a random equation in the pairing group. Okay, I see. So all that he does is verify here. He verifies the pairing. So here he's just saying this is how we define the proof, and then so if I send you the proof, the verifier using the pairing will be able to convince itself that indeed P of Z equal to Y. So that's what this section is doing. So I think before I get into this section, I want to first, I think, just give the intuition for what the proof is doing or saying, and also what the verification is doing. It's kind of simple, very simple once you've got it figured out. But I don't know, as I'm trying to explain it, I also realize that it's kind of tricky, and I'm probably uh, losing and confusing a bunch of you. I know I was certainly very confused the first time. So I apologize for this. So let me do kind of the simplest thing that we can do um, here, and is to just will forget for a minute the fact that we have the group, that we have the SRS points. We'll just do kind of the proof and the verification, assuming that we are actually like all of our elements, all of our information, all of our polynomials are just in the field. Um, and having this, we have addition, we have multiplication, so we can multiply polynomials, we can divide them, we can do whatever we want. So it's very easy. We'll be able to see what a proof is, but also what is the issue that arises from being in the field and why we actually need all this information to be pushed to the group for it to be secure. So so let's do this real quick. Okay. So again, what I was saying is let's forget about the elliptic curve for now. Um, and assume we live in FR. So we're just in the field. Okay, so what is a commitment? Oh, and also, so also for simplicity, uh, we assume that well, there's this S. Do we assume that we know S or not? I guess we can assume that we don't know. There is an S, but we don't know about it. Okay, so what is a commitment? Again, it's P of S. I guess the weird thing here is how do I even compute this if I don't know S? Okay, so let's assume that we know S, right? So we also assume that we know S. So obviously everything's going to be broken, but let's still see what happens. So and then uh, I want to claim that P of Z is equal to Y. So this is the claim I'm trying to make, and I'm trying to convince the verifier of this. So a proof for this claim will just be Q of S, which again, as we defined above, is just equal to P of S minus Y divided by S minus Z. Um, so you remember that Q of X was just defined as P of X minus Y, which is P of Z, divided by that linear term, X minus Z. So here all I did is I plugged S into the X's here. So we get this. We get this, and then the verification. How do I verify that this is indeed true? Um, so I'm the verifier. I you basically you give me all of this information, right? So the commitment is public information. Of course, I have access to Z and to Y because that's the thing that you're claiming. So you send me these two pieces of information. You also send me the proof Q of Z. So I kind of put all these things together, and all I do is I have this. So I have P of S, right? I have P of S, I have Y, so I do minus Y myself. This is me kind of doing this, and then I divide by, also I have S because we have access to it, and I have Z. So I do this, and then I check whether this is equal to the QS that you sent me, right? That's the verification, which is kind of very stupid. It's just basically I'm recomputing Q of S. Um, now the Well, so it's stupid, but also it is exactly the intuition that we want, right? So we'll basically be doing the exact same thing, but inside the group using the pairing with this multiplication. And actually, what we'll be doing is instead of dividing here by S minus Z, we'll be multiplying here, right? So this is actually, let's say this is actually the verification that we would be doing. So you take P of S, you do minus Y, and then you take Q of S, which you sent me, multiply this by S minus Z, and check whether these two match. And as we said, we'll be so that's the main thing, right? So in using the pairing in the group, we'll be able to I can take these elements, I can subtract, I can also multiply. Well, like I can't multiply, but through the pairing I can multiply. So we'll push all of these things to GT, right? And then in GT we'll check whether they're equal. That's kind of the main goal. That's the main kind of that's the gist of the idea here is when you I can push things down to GT to give me back multiplication in the field. Um, so, but forgetting about again about the group. So, what's the problem with this is that if or since I guess since S is known, um, then a malicious prover can prove any pair uh, Z, Y, right? It doesn't even have to be part of the polynomial. Works by sending, they just have to send, oops, P of S minus Y divided by S minus Z, which are all ingredients that they have. So basically what I'm saying is uh, that Y and Z don't even need to be related, right? By the evaluation of the polynomial. I can literally use any two numbers. I can make this work because here this equation will still hold. Um, so what is the solution to this? I guess the two problems is one that S is known, and then also this kind of the problem with S being known is that also the kind of um, the the malicious prover knows at which point kind of it'll be evaluated, so it can just it could also kind of create a polynomial that actually evaluates to this if it wanted to. So the solution is, of course, S is unknown, and that's what the SRS points are doing, and also in Q of S binds like by submitting Q of S, um, it binds the prover to all values of Q. Um, right. So again, we're using the binding property of the pairing. So so again, it's not really related to this, but it's related to what's actually happening is by sending Q of S, I'm actually binding myself to all of these values. And therefore, if you choose, you will choose a P and an S. Sorry, the S is kind of chosen. You can think at random, and then I will evaluate the P of S and Q of S. And because those can only match at up to the number of SRS points, 2 to the 28, there will be like a lot more points where Q and P don't match. So this will work. Um, and I mean, this is equivalent to other sampling schemes where if the S was just picked arbitrarily after the fact, that would also work. In this case, it's just the S is kind of chosen ahead of time, and then the powers of S are embedded. So this secret element at which we're sampling all of our polynomials is kind of chosen ahead of time, but it's secret, therefore nobody knows, so therefore nobody can break the the assumption. So okay, if we go back to the Kate proofs section. So let's see how Dankrad explains it, which is basically what I was saying, or trying to say at least. Mm, but okay, so what he's saying is here, so the verifier verifies this. So again, the proof is still just the it's the embedding or the commitment of Q evaluated S. And so the verifier verifies E pi. So what is pi? Pi is, is this is just Q of S. And the commitment, what is the commitment? It's P of S, right? And H is just the generator in G2. Um, so, so what he's saying here is that all of these things are available to the verifier. So you can read this paragraph. Of course, like Q is available. Um, S minus Z, S minus Z is just S minus Z. So this we have access to because one of the SRS elements. I embed Z using the same thing. So this is just Z times the generator, and then I do the subtraction in the group. So this I have access to this as a verifier. Um, I can do the same with Y here, and I have access to the commitment. So these are all things that I have access to. I just put them in this shape. I verify both pairings if they match. So the pairings are again sending stuff to GT. If they match, if the group elements match in GT, then the proof is correct. Okay, so then the question is why does this work? So we need to prove two properties, what he's saying, the correctness and the soundness. Um, and okay, so the correctness just means that as a prover, uh, if I follow the steps properly, I can actually correctly convince the verifier that that is the correct point. And as he says, this is usually the easy part. Um, and soundness is the property that a malicious prover cannot kind of break the scheme and then trick the verifier into believing a fake associations. Okay, so he says let's start with the easy part, which is the correctness. So we verify this, which again, if you remember, this is just a rewriting of this as we define somewhere up here. Yeah, using this right here. So we're using this equation. It's just like playing with the notation. So it'll be hard to follow me, but if you just like stop the video and pause it and actually write it down, you'll see it's pretty simple stuff. But right. So what he's saying here is just that so we have above e pi is s minus z2, and what is this is just equal to e of the generator and h of qs times s minus z. That's just what this is, and this again we have defined this other nice notation that this is just q of s times s minus z t. Right. So again, it's like I have these elements in G1 and in G2, and I can, using the pairing, push them over to GT. And inside GT, I kind of get back this multiplication. So it's as if I can multiply polynomials. And again, what does multiplying polynomial give us? It gives us that I can verify this equation very easily by putting this on the other side. Right? This is the x minus z is the, so I have this and I can verify that this QZ matches this P of x. Um, I mean, so this is it, right? This is basically it for correctness. And then for soundness, so for soundness, what did you say? Something tried to work. Ah, I see. So, okay. Okay, so he's saying here that if they want to break the scheme, they could choose a y prime that is not p of z, but then this is not divisible by x minus z because there's no zero at z if you do this. So you just can't perform the polynomial division. Um, but that, I mean that's just kind of some intuition. It doesn't mean that there's no and there's not another way, which is what he says here. So the other way would be if they can compute this somehow by doing this. Um, just do anything you want. Right. Okay. So yeah, again, I guess we're we can also kind of skip this. What he's saying, this is hard to prove, and you need something about the so-called the Q strong SDH assumption, where SDH I think is a strong Diffie-Hellman, and the Q is the fact that you not only have like two elements that you know in the group, you have Q of them, which are all the SRS points. So we have, let's say, 2 to the 28 SRS points. Even given all of this, I can't reconstruct S. Right. So all of these proofs are kind of based on me not knowing S or the malicious prover, because if S turned out to be known, then I could, of course, create, it would be easy to create a polynomial Q, right? I could create any polynomial that, I could create any other polynomial that, well, sorry, so let's say I knew that S is equal to minus, I don't know, 3, let's say, right? Then I could just create any polynomial, malicious polynomial, whatever. I could create any polynomial, Q prime, whatever, that goes through S, and I would be able to break the scheme. Okay, so that's the idea. The last part is multi-proofs. So I'm realizing this video has been pretty long. But multi-proofs are extremely important to EigenDA. They're also kind of the ultimate succinctness argument. So it's all that we've been doing right now is just opening a single point at a time. Um, if you take Let's say you take a Merkle tree, you can always, I can open multiple elements by sending you multiple branches. So multiple Merkle proofs kind of. So what you can do actually, the thing with these Merkle proofs, with these Merkle branches, I have two branches. Sometimes, like they couldn't start with have a joint kind of path. So maybe you can amortize some of the cost there, but mostly you'll just have like two separate, entirely separate proofs. Whereas with KZG commitments, you can actually add them. And not only is the proof going to be the same, so the proof is going to be the same, like a single element size, right? It's still like a QS. You're going to have the same a Q of S for another polynomial. It's also going to be a single G1 point, so 32 bytes for the proof. Um, and verification is also like very fast. So I can open as many points as I want on the polynomial. I can convince you that the polynomial evaluated to, many different points with a single size element proof. So that's what he's saying here. Right. Okay, so yeah, so that's kind of what he's saying. Oh, right. Okay, so wait, sorry. So I was skipping one important part, which is that the toy example of using Merkle trees as polynomial commitments would have needed to send 2 to the 28 elements, all the coefficients of the polynomial. Right, so you remember what he was saying here, and then again, as I said before, so this 2 to the 28 field elements, this is every field element, let's say in BN, let's say BN254, which is what we use, is 32 bytes. So this is just 2 to the 33 bytes, which is 8 gigabytes. 8 gigabytes. So 8 gigabytes is actually the size of our SRS G1 points for eigenvalue. Okay. So anyway, so we have this. Okay, so this is like we're almost done here. We're almost done. So how does a multi-proof work? I'll give the intuition briefly. Um, the idea is kind of simple. It's just, what you were doing for the proof for for reveal a single element was just that I subtract P of X um, by the evaluation, by that point, by the constant evaluation at Z. I have Y, I subtract the polynomial and make it go through 0 at that point. And that means I can divide the polynomial by, the linear factor. Um, and then that gives me a degree d minus 1 polynomial q, which I can evaluate at s, and that gives me the embedding. So what we do in this case is is pretty much the same thing, right? So I have n points that I want to open, and so I mean, it's a bit harder because you can't just do it iteratively. You need to use this interpolation kind of polynomial. But the idea is the same, is that you'll kind of divide the polynomial by this other polynomial that will reduce its degree by the number of elements that you're trying to reveal. So let's see what this is. So okay, this is actually like very, very, very simple stuff. If you've never seen it, it's worth, I don't know, finding a video on YouTube or something. But written like this is very scary. But all that this is doing is that this stuff is basically just the Lagrange basis Li of x, which is a polynomial that uh, evaluates at if we say zk, that evaluates at it's the Kronecker delta. So it's basically, it means that this is 0 if, well, it's 1 if I equals to k, and 0 if else. Um, so, I mean, right, and you can, so all that it's saying is just I have these, I create this polynomial out of these Lagrange bases, which is just a polynomial. So, okay, let me draw this. Maybe I should have done. Let's say we have 3 points, so here, here, and here, right? And so the okay, these are my points. So let's say Z0, Y0, what's the point? Z1, Y1, and Z2, Y2, which I'm trying to open. So now let's define, let's say the Lagrange L1. So L or L0, sorry, will be, let's say this is one. So this, I, I basically like this is the idea, right? So I just like I create a polynomial, which is literally this, just like this polynomial Li of x, which is a polynomial that is one at the first point. So this would be this is L0 of x. That is it's one at z0 and it's zero at both other points in that I'm trying to reveal. And then I create polynomials like this for all the other ones. So um, let's say L1 would look the opposite. It would look something like I mean it's kind of hard to draw because they're polynomials, so they wouldn't look like this, but you know the idea is this is L1 of x. And anyway, so you can see that what these polynomials do is I can just add them up with the yi coefficient because L0 of y0 is just gonna take this polynomial y, the red polynomial multiplied by y, zero will just make this will give this polynomial. But it's still zero at all the other points. Um, and then the same thing for the green ones. So basically all that I have at the end is I have a polynomial. I don't know why I'm going through all of this. All that this does at the end is just it literally just creates a polynomial I of x, which literally goes through these 3 points. Right. So anyways, I'm sorry I babbled for so long. That's all that I'm trying to do, trying to explain the construction. But at the end of the day, if you don't understand this, just think about it conceptually as literally it's called the interpolating polynomial because it's a polynomial that goes through these 3 points. Um, and then once we have this, then you play the same trick, right? So you have p of x, you do minus I of x. So we subtract the polynomial such that now we know that p of x has zeros at all of so p of x and I of x are both equal at these points, meaning that if I subtract p of x, I subtract I of x from p of x, I know that this resulting polynomial is the is zero at all of the z points that I'm trying to open. Therefore, I can divide it by this zero polynomial, which is I can divide it by all of these coefficient. Um, right? So it's literally the same trick. And then I get qx, which here is a degree um, d minus k polynomial. And then again, the same trick. So the commitment, the how would we say? So the commitment to z0, y0 to all of these points. Well, sorry, no, that's not true. So the proof pi is equal to the commitment q of s, one the same way. Um, and the commitment is still the commitment is still just the uh, the polynomial evaluated s. Um, and then to verify this, I play the same trick again that we had. And so you have your proof, you have then you have the commitment, and here you use so everywhere that before we were using kind of the value of I, now I need to replace it by polynomials. So namely these two things replace what we had previously, which was just uh, which was what was this? This was the single one that we were opening. So this was s minus y, if you remember, and this here was it's just the value, so it's, c minus y, I guess. I guess what's the notation he's using? X. So he's using I think p of z equal y, right? So it's actually the opposite. So this was minus z, and this would be y. And then, okay, so you get to the same thing. And then you verify it with this formula, and this formula again, what is it checking? It's literally checking that this equation holds. The same trick. So we're done. We have sync proofs. We call them multi-reveal proofs. that's the idea. And then the last, I promise, chapter is just Kate as a vector. Oh, so here he's just saying that, um, so we've talked about we have Merkle trees that are kind of typically used to commit to a vector. We can use them to commit to a polynomial by putting the coefficient of the polynomial as the leaves of the tree. That's kind of stupid for all the reasons that we listed. Um, Whereas in the case of KZG, what we have is we have a polynomial commitment. But what he's saying is we can a polynomial commitment is just strictly stronger than a vector commitment. So given the kate, like given a polynomial commitment, of course I can use this as as a vector commitment. Um, and the way that you do this is just that if I had a if I oops. So if I have a vector, let's say I want to replace a Merkle tree that I had with, let's say, E1, E2, E3, E4, sorry. Um, then I just put these as I just construct a polynomial, which at any points that I choose, so what does he say here? He says I, so let's say like I being 1, 2, 3, 4. I'll just put the values E1, E2, E3, and E4. Right? And then there's a polynomial that goes through these guys. And so again, it's just the trick of the interpolating polynomial. So if I have data, I put them as the value of a polynomial, and I get the interpolating polynomial, and then I can play the same trick. Right now, I have a polynomial, so I'm actually, I'm actually committing myself to a lot more. I'm committing myself not only to these four guys, but also to all the other values. But if they don't matter to me, I can still use the polynomial to commit to them. Um, and the nice thing is that I get proof aggregation, right? So here he says the Merkle proof would cost log n hashes to even just prove one element, whereas in this case, in the case of the KZG commitment, it's a single item. And the same way, if I want to reveal multiple elements, if I want to reveal, let's say this guy and this guy, then I need to give kind of two, two branches, and for this guy, kind of this and this, right? So I basically need to reveal the whole tree, whereas with the KZG, again, the same thing. I can reveal one item, I can reveal two, I can reveal all of them. It's all only ever going to cost me a single 32 byte item, um, and a bit of time on the prover side. Of course, the bit of time is longer because verifying, computing a pairing, well, two pairings and some group operation is always going to be longer than just hashing up the tree. So that's kind of the trade-off you're making. Ultimately, you have even more succinctness of your proofs and commitments. Um, at the cost of a little bit of extra verification time and prover time, of course. Um, awesome. Okay, so this is the paper. I hope some of it made sense. What I plan to do in the next video is to go over, there's another paper of Dankrad. Okay, so where is this Kate proof, sorry. So the multi-proofs, okay, so the multi-proofs are here. Right, okay, so this thing, this beauty right here. Right? So this thing is the multi-proof. The problem is that computing this is not that easy. It's nice when you write it as math like this, but when you actually want to compute it in practice, it's not that simple, especially if you want to compute multi-proofs, multiple of these together. So Dankrad has a follow-up paper called the fast amortized Kate proofs, which explains. So if this was a theory paper, then the next one is kind of the implementation paper, is how do we actually compute this in practice on a computer, doing it fast. And this paper is exactly what we implement for the EigenDA code base to prove that the data that every validator is receiving is actually, it's sharded. We call them chunks, but it's basically it's correct. The shards of data that it receives from the entire blob actually belong to the commitment that the client is committing to with the data. All right, so I'll see you in the in the next video where we go over this paper. I hope this made sense.